Development of In-Situ Resource Utilization ISRU technology by 2025, for key innovations for sustainable Mars colonization. Introduction. The quest for sustainable human colonization of Mars is one of the most ambitious goals of modern space exploration. As we move closer to this reality, the development of In-Situ Resource Utilization ISRU technology emerges as a critical focus. ISRU refers to the practice of harnessing and utilizing local resources available on celestial bodies, thereby reducing the need for extensive supply missions from Earth. By 2025, several key innovations are anticipated to revolutionize ISRU capabilities, facilitating a sustainable human presence on Mars. 1. Resource extraction technologies. A cornerstone of ISRU is the ability to locate and extract resources essential for human survival and mission sustainability. NASA's ongoing efforts in resource extraction technologies are pivotal for Mars colonization. Lunar and Martian exploration missions. The Volatile's investigating polar exploration rover Viper is set to explore the Moon's south pole in 2023, aiming to identify and map water ice deposits. The water ice found could be vital for drinking water, oxygen production, and even fuel for rockets. Mars Oxygen In-Situ Resource Utilization Experiment MOXIE, launched aboard the Perseverance rover. MOXIE aims to produce oxygen from the carbon dioxide-rich Martian atmosphere. Successful operation of MOXIE is crucial as it demonstrates a method to generate breathable air and propellant directly from Martian resources. These missions underscore the importance of not only finding but also efficiently extracting resources like water and oxygen, which are fundamental for sustaining life and enabling further exploration. 2. Additive Manufacturing and Construction. The advent of additive manufacturing or 3D printing represents a significant technological leap in ISRU. This innovation allows for the construction of habitats and other structures using local materials, dramatically reducing reliance on Earth-supplied components. Utilization of regolith. NASA is exploring the potential of using regolith, the loose material covering the lunar and Martian surfaces, in construction. This involves developing technologies to process regolith into building materials capable of withstanding harsh extraterrestrial environments. Partnership with U.S. Army Corps of Engineers. NASA's collaboration with the U.S. Army Corps of Engineers aims to enhance construction capabilities by leveraging in-situ materials. This partnership focuses on advancing technologies for excavation handling and 3D printing to create sustainable living environments for astronauts. Challenges and innovations in 3D printing. The challenges of building in space include creating structures that can endure radiation, temperature fluctuations, and dust storms. Ongoing research and development in additive manufacturing techniques will be pivotal in addressing these challenges and ensuring the viability of habitats on Mars. 3. Energy generation through solar power. Energy is a critical component of any long-term mission in space. As human exploration of Mars extends, there is an increasing need for reliable energy sources to support ISRU operations. Solar energy utilization. Solar power has been a reliable energy source for spacecraft for decades. The Gateway project, which includes solar arrays for power generation, illustrates the potential of solar energy in supporting sustainable operations in deep space. Integration with ISRU operations. The successful extraction and processing of local resources will require significant energy input. Thus, integrating solar power solutions with ISRU technologies is essential for ensuring that energy demands are met sustainably. Future energy solutions. Beyond solar, NASA is exploring other energy generation methods to support ISRU activities, including potential nuclear power solutions. This diversified approach will enhance the resilience and reliability of energy supply for future Mars missions. 4. International collaboration and knowledge sharing. The complexity of Mars colonization necessitates a collaborative approach, combining expertise from various global partners. Joint missions and data sharing. NASA actively collaborates with international space agencies and academic institutions to enhance understanding of lunar and Martian resources. Joint missions like those aimed at exploring polar volatiles facilitate knowledge sharing and improve ISRU technology effectiveness. Coordinated research efforts. International collaboration extends to research efforts focused on resource extraction and utilization. By pooling resources and expertise, space agencies can accelerate advancements in ISRU technologies and share best practices for sustainable exploration. Building a global knowledge base. Collaborative studies and missions contribute to a growing body of knowledge about the accessibility of resources on Mars and the technologies required to utilize them effectively. This shared knowledge is crucial for preparing for future human missions. Conclusion. The pathway to sustainable Mars colonization hinges on the successful implementation of ISRU technologies. By 2025, NASA and its partners are expected to make significant strides in resource extraction, additive manufacturing, energy generation, and international cooperation. These innovations not only aim to support human life on Mars but also lay the groundwork for future explorations beyond our planet. The integration of local resource utilization will fundamentally change the dynamics of space exploration, making long-term missions more feasible and less dependent on Earth. As we move forward, the collaborative efforts in advancing ISRU technology will be critical in realizing the dream of human colonization of Mars, ensuring that humanity can not only visit but also thrive on the red planet. The content provided discusses the development of in-situ resource utilization ISRU technology, crucial for sustainable Mars colonization by 2025. Here are some counterintuitive insights derived from the text. 1. Reliance on local resources versus Earth supplies. While one might assume that long-duration space missions would necessitate comprehensive resupply missions from Earth, the text emphasizes that reducing reliance on Earth supplies through ISRU is essential for sustainable exploration. This counters the common belief that space missions can simply rely on continuous supply chains from Earth, highlighting the need for self-sufficiency. 2. Solar power as a primary energy source. The content indicates that solar energy, often seen as a limiting factor in deep space missions due to distance from the Sun, is actually a cornerstone of ISRU efforts. This challenges the perception that solar energy is impractical for long-term missions beyond the inner solar system, suggesting instead that it remains a viable, reliable energy source even in challenging environments like Mars. 3. 3D printing surfaces versus transporting materials. The innovative use of 3D printing additive manufacturing to create structures from local regolith might seem less feasible than transporting prefabricated materials from Earth. However, the text suggests that utilizing local materials through advanced manufacturing techniques is not only more efficient but may also be essential for establishing habitats and other structures on Mars and the Moon. 4. International collaboration as a necessity. The article presents the idea that international collaboration is a key component of ISRU development. This may seem counterintuitive, as one might expect that space exploration would be primarily driven by individual nations. Instead, the text posits that sharing knowledge and resources among global space agencies is vital for enhancing the effectiveness of ISRU technologies. Promoting a more cooperative approach to space exploration. 5. Water and volatiles as valuable commodities. The emphasis on extracting water and volatiles for sustaining life and propulsion might lead one to think that these resources are scarce or impractical to utilize. However, the research indicates a wealth of potential water sources on both the Moon and Mars, suggesting that these essential resources are more accessible than previously believed, fundamentally altering the perception of what is necessary for human survival in space. These points illustrate the complexity and nuance of ISRU technology development, highlighting innovative approaches that challenge preconceived notions about space resource utilization and exploration. The development of in-situ resource utilization ISRU technology is a pivotal aspect of the plans for sustainable Mars colonization by 2025. While many reports and discussions focus on the overarching strategies and technologies, Several critical nuances often overlooked can significantly impact the feasibility and success of such ambitious endeavors. Here are some of those important details and their significance. 1. Understanding local resource availability. A fundamental aspect of ISRU is the accurate identification and characterization of local resources on celestial bodies. While NASA's missions such as Viper and MOXIE are set to explore these resources, the current understanding of the location, concentration, and form of these resources is still incomplete. For instance, while it is known that water ice exists in certain regions of the Moon and Mars, the specifics of its distribution can drastically affect extraction strategies. The significance of this lies in the fact that without precise data on resource availability, missions could either overestimate the potential for sustainable living or conversely face dire shortages of essential supplies. 2. Technological readiness levels (TRLs) for ISRU systems. The advancements in ISRU technologies are often discussed in terms of their conceptual frameworks and initial tests. However, the readiness levels of these technologies for actual deployment in space missions are crucial. Many technologies, while promising in laboratory settings, may not yet be at the TRL required for prolonged space missions. This gap can lead to reliance on untested systems during critical missions, which could jeopardize crew safety and mission success. Understanding the current TRL of various ISRU technologies is essential for planning and ensuring that reliable systems are in place before human missions commence. 3. Regolith processing and construction challenges. The use of regolith for construction and resource extraction is a cornerstone of the ISRU strategy. However, the challenges associated with processing regolith into usable materials are often underestimated. The physical and chemical properties of regolith vary significantly between the Moon and Mars, which can impact the effectiveness of extraction and construction technologies. For instance, the presence of fine dust on the lunar surface can lead to equipment clogging and wear. This detail is significant because it underscores the need for tailored technologies and methods that account for the unique environmental conditions of each celestial body rather than applying a one-size-fits-all approach. 4. Energy requirements for ISRU operations. While solar power is highlighted as a primary energy source for ISRU operations, the actual energy requirements for extracting and processing local resources can be substantial. The energy-intensive nature of these processes might not align with the available solar energy, especially during long Mars nights or in areas with limited sunlight. This highlights the importance of developing energy storage solutions and alternative energy sources such as nuclear power to ensure continuous operation of ISRU technologies. The significance of this consideration is that it can lead to the design of more resilient and adaptable mission architectures that can operate effectively under varying conditions. 5. International collaboration and knowledge sharing. The report emphasizes NASA's collaborations with international space agencies and academic institutions. However, the depth and breadth of knowledge sharing are often superficial in discussions about ISRU. The integration of diverse scientific and engineering expertise from various countries can lead to innovative solutions to complex challenges. The significance of this collaboration lies in its potential to mitigate risks and enhance the efficiency of ISRU technologies. For example, joint missions could combine resources and expertise to tackle specific challenges related to resource extraction and processing that a single agency might struggle to address alone. 6. Psychological and social aspects of long-term ISRU missions. The focus on technological and logistical aspects of ISRU often overlooks the psychological and social dimensions of long-term missions on Mars. The ability to utilize local resources will significantly affect the mental well-being of astronauts, as it can foster a sense of self-sufficiency and reduce dependency on Earth. However, the psychological impact of isolation, resource scarcity, and the challenges of living in an extraterrestrial environment must be considered in mission planning. The significance here is that successful colonization will not only depend on technology but also on ensuring the crew's mental health and social dynamics. 7. Regulatory and ethical considerations of ISRU. The ethics of utilizing extraterrestrial resources is a topic that often receives limited attention in technical discussions. As nations and private companies prepare for ISRU, it is crucial to establish international regulations governing the extraction and use of resources from celestial bodies. The significance of this is twofold. It can prevent conflicts over resources and ensure that the exploration and utilization of these resources are conducted responsibly and sustainably. A clear framework for ethical considerations will be essential for fostering cooperation among nations and stakeholders involved in space exploration. 8. Adaptation of ISRU technologies for Earth applications. While the primary focus of ISRU is on Mars colonization, the technologies developed can have significant applications on Earth, especially in remote or disaster-stricken areas. The ability to extract resources and produce necessities locally can revolutionize how we manage resources on our planet. This crossover potential is often overlooked but is significant for garnering broader support and funding for ISRU research and development. Highlighting these terrestrial benefits can enhance public interest and investment in space technologies. Conclusion. The path to sustainable Mars colonization through ISRU technology is fraught with challenges that extend beyond mere technological advancements. The nuances discussed, ranging from the intricacies of local resource identification to the psychological well-being of astronauts, highlight the complexity of this endeavor. Each aspect carries significant implications for mission planning, execution, and long-term sustainability. Recognizing and addressing these often overlooked details will be crucial for overcoming the hurdles that lie ahead in humanity's quest to become an interplanetary species. 1. Resource extraction technologies. The identification and processing of in-situ resources such as water ice on the Moon and oxygen from the Martian atmosphere are fundamental to sustainable Mars colonization. NASA's missions like Viper and MOXIE are critical in mapping and utilizing these resources, ensuring that future astronauts have access to life-sustaining materials and fuel, thereby reducing the need for resupply missions from Earth. 2. Additive manufacturing and construction. The integration of 3D printing technologies into ISRU strategies allows for the construction of habitats and other essential structures using local materials such as regolith. This innovation is vital for establishing self-sufficient living environments on Mars, as it minimizes the logistical challenges and costs associated with transporting construction materials from Earth. 3. Energy generation through solar power. Solar energy remains a primary and reliable energy source for space missions. Projects like the Gateway will utilize solar arrays to provide the necessary power for ISRU operations. This energy is crucial for processes such as resource extraction and manufacturing, thus supporting sustainable operations and long-term human presence on Mars. For international collaboration and knowledge sharing, the success of ISRU technologies is enhanced through international partnerships and collaboration with various space agencies and academic institutions. Joint missions and data sharing initiatives improve the understanding of extraterrestrial resources, facilitating the development and implementation of ISRU technologies for broader and more effective exploration efforts. 1. Apollo Program 1961–1972. The Apollo program was a series of space missions undertaken by NASA, aimed at landing humans on the Moon and bringing them safely back to Earth. Apollo 11 in 1969 marked the first successful manned moon landing. The program highlighted the importance of utilizing local resources as astronauts used lunar materials for various experiments and analyses. The missions demonstrated the feasibility of human exploration of extraterrestrial bodies and set the groundwork for future resource utilization in space exploration. 2. Mars Pathfinder 1997. This NASA mission included the Sojourner rover, which was the first successful robotic rover to operate on another planet. Mars Pathfinder's success relied heavily on the in-situ analysis of Martian soil and rocks. The mission gathered crucial data about the Martian environment that can inform future ISRU efforts, especially regarding the availability of resources like water and carbon dioxide, both of which are essential for supporting human life and fuel production on Mars. 3. International Space Station 1998-present. The ISS serves as a unique laboratory for studying the effects of long-duration spaceflight on the human body and for developing technologies that will be necessary for future missions to the Moon and Mars. It has demonstrated the potential for recycling water and air utilizing local resources to sustain human life in space. The ongoing research on the ISS plays a vital role in advancing ISRU technologies, as it provides practical insights into the challenges of living and working in space over extended periods. Future outlook: development of In-Situ Resource Utilization ISRU technology by 2025. The development of In-Situ Resource Utilization ISRU technology is pivotal for enabling sustainable human colonization of Mars by 2025. This technology focuses on utilizing local resources on celestial bodies to reduce dependence on supplies from Earth. By harnessing Martian and lunar materials, ISRU not only supports human survival but also enhances the feasibility of long-term missions. The following 4 key innovations are expected to drive ISRU advancements. 1. Resource extraction technologies. By 2025, significant progress is anticipated in resource extraction technologies, particularly in identifying and processing local materials. NASA's Viper mission, set to launch in 2023, aims to explore the Moon's south pole for water ice, which is critical for sustaining human life on Mars. The Mars Oxygen In-Situ Resource Utilization Experiment MOXIE is expected to demonstrate the production of oxygen from the Martian atmosphere. These technologies will lay the groundwork for future crewed missions, highlighting the importance of local resource utilization for life support and fuel production. 2. Additive Manufacturing and Construction. Advances in additive manufacturing, particularly 3D printing, are projected to transform habitat construction on Mars. By utilizing local regolith, astronauts could create structures essential for living and working on Mars. Collaborations between NASA and the U.S. Army Corps of Engineers focus on developing construction capabilities that leverage local materials. This innovation is crucial for establishing self-sustaining habitats and reducing the need to transport building materials from Earth. 3. Energy generation through solar power. Solar energy will continue to be a cornerstone of space exploration. The Gateway project, which includes solar arrays for power generation, exemplifies how solar energy can support sustained operations in deep space. By 2025, solar energy systems are expected to be further refined for use in ISRU applications, providing the necessary energy for resource extraction and processing activities on Mars and the Moon. This reliable energy source will be vital for enabling autonomous operations without constant resupply missions from Earth. 4. International collaboration and knowledge sharing. Collaboration among international space agencies, academic institutions, and private industry is expected to enhance ISRU technology development. By sharing data and resources, these partnerships can accelerate the understanding of lunar and Martian resources. Joint missions and collaborative research efforts will improve the overall effectiveness of ISRU technologies, fostering a global approach to space exploration. Key points of consensus. A common theme across all sources is the necessity of ISRU for long-term human missions beyond Earth. The critical role of local resources such as water and oxygen in sustaining life and fuel needs is emphasized. Innovations in resource extraction and manufacturing technologies are seen as essential for enabling sustainable exploration. Differences in sources. While detailed insights from NASA's initiatives highlight specific missions and ongoing technological advancements, other sources that were inaccessible might offer additional theoretical frameworks or case studies that could further inform ISRU development. Nonetheless, the overarching focus remains on current missions and technologies that pave the way for sustainable human presence on Mars. Timeline of events. 2023 – Launch of the Viper mission to explore the Moon's south pole for water ice. 2021 – Launch of MOXIE on the Perseverance rover to test oxygen production on Mars. Current, ongoing research and development in ISRU technologies including excavation and processing of regolith additive manufacturing and solar energy utilization. In conclusion, the future of Mars colonization hinges on the successful implementation of ISRU technologies. By 2025, NASA aims to establish a solid foundation for human life on Mars, leveraging innovative resource extraction construction methods and international collaboration. These advancements will not only facilitate sustainable human exploration of Mars but also mark a significant step toward humanity's future in deep space.